All right, in this video, we're going to compare the averages or means of two groups using a t-test to see if the difference between the two means are statistically significant. We'll work off of the same file that has been in some of the other videos, so if you have it and want to follow along, you can. But let's just say that we had been in our HR file exploring some things, and while working on some pivot tables, we came across some differences that we thought were interesting. For example, maybe we thought that the monthly income of people who worked overtime versus did not work overtime might be different. And so we chose to look at their averages. So monthly income, and we're curious by department. When we see this, we notice that, and we are talking about a monetary value, we notice that individuals who do not work overtime seem to have lower monthly income averages than those who do work overtime. And we see that across all of the departments, but it looks like the difference in HR maybe is a noticeable difference. Those who don't work overtime seem to make about $6,423 on average. Those who do work overtime seem to make about $7,281 on average. And so our question is, I see that they're different, but are they statistically significantly different? Or is this just kind of due to chance? Maybe if some employees had quit, we'd see it go away. Maybe there's some outliers pulling some things in different directions. So the way to test whether this difference is not just due to chance or not likely to be due to chance is to use a t-test. So let's say that we have just a file on the monthly income of each person in the HR department. Okay, and let's just say that after some data cleanup, we limit ourselves to just the data of monthly income, with one set of the monthly income values for those individuals who had no listed as their overtime, and another set of data for those individuals who had yes listed as their monthly income. Now, I've set these up as two different lists because they're different people. They're the people who had no overtime, the people who had overtime. And we can see that there were different quantities of people in each of these categories. By looking at the data, we can see that we had 46 individuals with no overtime and 17 individuals who had overtime, and these are each of their respective monthly incomes. Now, if you already know about t-tests, there is a really fast way to put it in as a formula. So for those of you who know about t-tests and know which ones, just not how to do them in Excel, a very fast way is the following formula. If you don't know about t-tests yet, just wait 30 seconds and then I'll give you a better way to go about this. So a fastest way for those who know how to do it, do equals for a formula. You'll see these ones pop up. We want to select t-test. It's going to ask us which data, and we're going to say, I want the data from those who don't have overtime, and I want to compare it to the data of those who do have overtime. It's going to ask which tail do you want. Since I already have an assumption about the direction, I'm going to do a one tail. And since these are different groups of people, I'm going to do two tail. You can do an F-test to find out whether the variances are equal or unequal. When in doubt, I like to do unequal. So I will just go ahead and put that in. And that will be your p-value. And you can assess that p-value to see whether or not the differences are statistically significant. So for those of you with a background at already understand t-test, this is how you can do it very quickly in Excel. For those who are just learning t-tests or maybe haven't gotten into it as much, I don't recommend this route. And if that didn't make sense to you, that's okay. This is for when you get there later, after you feel really confident and comfortable doing t-tests. What I recommend for you now, if you're new to this, is to use the data analysis tool pack. Now, you will have to make sure that you've downloaded it in Excel. You can do that by going to File, Options, Add-ins, and making sure that you have the data analysis tool pack added and turned on. If you have it on, you'll see it under the data ribbon, and you'll see a data analysis option here. When you click it, it will show you all the lovely things that the toolpack can do for you, and you'll want to scroll until you can find the t-tests. Now, when you get here, you might be a little confused because there are 3 different t-tests. How do you know which one to pick? Well, the first question is, do you have paired or unpaired data? Paired data means there's something connecting the two pieces of data that you want to compare to each other. So in a people file, what's really common might be something like maybe you have employee data about someone before and after training, and you want to see whether or not they got statistically significantly higher scores after training. You would take the same one person score on the first measure and then the same person but a second measure. Because it's the same person, they would be paired. And so in that case, the math can take that into account. It can say, hey, I understand that like certain people, might score lower, but then get better after training. But somebody who was already really high might get even higher after training. And so it's going to take into account the fact that the data is paired in some way. If you've got two completely different groups of data, for example, employees who do work overtime and employees who do not, and they are not the same employees at all, which is true in our data set, then we have two samples and they are not paired. So we're going to have to choose one of these two sample tests. Then you just have to go for, do I want equal variances or unequal variances? This is a question about how similar the different data points tend to be in terms of closeness to the average. If you don't know, I recommend just using unequal variances because of how it works in the math going on. You can do something called an F-test to test whether it's equal or unequal. When in doubt, I recommend using unequal variances. So we'll go ahead and choose this one because we have two samples and we're just going to assume unequal, and we'll press OK. And Excel says, great, which two sets of data do you want me to compare? And so I'm going to tell it that I want to compare in range 1 those who do not have monthly income. And I can use this fun little grabber to start here. I'm going to choose to start with the title and go all the way down. If you don't have a title, that's okay. And I've got that now selected. And then it says, okay, what thing do you want me to compare it to? What's the second set of data? So I'm going to go ahead and compare it to those who do have monthly income, do have overtime, and select their monthly income. Now, because I started at row 1, which is just words and not numbers, I need to make sure that it knows I have labels in here. Because if not, it's going to try to calculate that text as a value and it's going to get all weird. You also want to be really careful that if you do just start from data with no titles, that you don't check this. You do not need to fill in the hypothesis mean difference. This is just asking if you have something that you think will be there. By default, it uses 0. And we are saying that we want to see whether or not these differences are significantly different than 0, meaning that they aren't the same. Alpha is default here set at 0.05. That's a great one to leave it at. Remember, alpha is something that we want to compare our p-value to. If our p-value comes in below our alpha, we can call it statistically significant. Now down here, if you don't change anything, it will just pop out your results into a new tab. I'm going to go ahead and tell it to give us our output right here in our sheet so we can see it next to our data. So I'm going to click a spot for the output, and when I press OK, it will give us our outcomes. So here we have a nice titled table. We can see what t-test we chose. We get some different data points on our first variable of no overtime, and then our second group of yes overtime. We can see their averages. We knew this already because we saw it in the pivot table, but we can see that the average for those who don't have overtime is lower than those who do have overtime. We can see the variance. This is just a measure of how different the values tend to be from their average. We can also see how many different data points were used here. This is a nice double check for you to make sure that you did grab the right data. Make sure those observations match the number of data points you expected there. We are just testing whether or not the difference is not 0. Degrees of freedom helps us understand how much additional error or movement there might be if there were different data points in our sample. And then it gives us our real t-test outputs. You get a t-statistic, which is a value that gets compared against a table that is preset and based off of degrees of freedom. We don't have to get into what the t-stat is or how to read it. for our purposes today. But what you will want to look at is the p-value. Now it's going to give you two different t-stats and p-values. You're going to get a one-tail t-stat and p-value, and then you're going to get a two-tail. And these are going to be used for whether or not you think you are going to look in one direction or two directions. What I mean by that is if you already think that the difference exists in one direction, for example, we already think that the monthly income for those who work overtime is higher than those who don't, that implies a direction. And if you use a one-tail test, you're basically telling the math to just look that way. Just go test if overtime people do significantly make more monthly income on average than those who don't. If you were to tell it two-tail, that's your way of saying, hey, I don't know which way you should look. Why don't you look both ways? Why don't you see if it's bigger and why don't you see if it's smaller? Typically, because you can look at the averages before, you might have an assumption and you could use the one-tail. I'd do that. What you'll also notice is the one-tail p-value is always going to be half the size of the two-tail. And that's because what it's basically doing is taking the probability of finding a difference of this large or larger and splitting it in half. So if we look at our one-tail p-value, we see that we got a value of 0.3. That is a lot bigger than our alpha of 0.05. So we would say in this case that there is not a statistically significant difference between those who work overtime and those who do not work overtime. And this can be both confusing and powerful. It might seem confusing because you're like, wait a minute, but there is a difference. This one is smaller than this one. And what your non-significant finding is telling you is, yes, there's a difference, but the probability that you got that difference just because of chance or that it might disappear, if one person left the company or a different person came in, is pretty high. You could expect it to be different, like 30 or 31% of the time. So you wouldn't want to make a big statement about people who work overtime, at least on this HR data set, always having higher average monthly incomes. It could change a little bit here and there. And the reason this is so powerful is that too often we rely on averages more than we should. And you might look at an average like this and then make statements like, well, if you want to make more money, you should work overtime because those people have higher average incomes. But you don't want to send that message if it's not always going to be true. You're going to be wrong a lot of the times. And so by not just talking about the average, but also talking about whether or not it is a statistically significant difference, you can have a more accurate and a more likely to be true in the future conversation about these kinds of differences. And that's why using the t-test is so powerful. It takes our averages and lets us know whether or not we expect to find a difference of at least that big or bigger in the future. And in our particular case here, we would say for the HR individuals that we're looking at, we would not necessarily always expect for those who work overtime to have higher monthly income averages than those who do not. It happens to be the case right now, but may not always be the case. And that's why we would say it's not statistically significant. And if you wanted to do this on paired data, for example, having before and after, the only thing you really need to do differently is to make sure that your data is set up with the paired items next to each other. So for example, a paired t-test data set might look something like having a value for employee number and then having the first thing that you want to assess, maybe test score at time 1 compared to, say, test score at time 2. And then you would have something like this that indicates, hey, this is the same one employee who got a 58 and then later got a 76. Employee number 2 might have got a 43 and then a 66, and so on and so forth. And so maybe we think that the test score was pre-training and this test score was post-training, and we want to see whether or not people got significantly better after training, we could take the same approach, but this time we would get a t-test with a paired setup, and we would follow our steps as last time. You do not need to include that employee in there, but you do want to make sure that they're next to each other when you put them in, so that when you say variable 1, range B 1 through 5, and then you put in C 1 through 5, Excel is going to assume that the ones next to each other are the pairings by putting them in the same row. So you need to make sure your data set like this, not with two different tables that would need to be right next to each other or at least on the same rows. And Excel is going to use that to pair them for you. So we'll go ahead and do labels again. Output, we'll put it right here. And you'll end up getting an output similar to like what we saw last time, except that now it is assessing the pairs. We'll say that the average for time 1 was 49.25, the average of time 2 was 70.5, and we'll check our one-tail t-test because we think that people will get better after training. And in fact, we find that we have a very small p-value. It's definitely below 0.05. And if this was our data set, we would say, yes, we believe that the training had a statistically significant difference in improving individuals' test scores from time 1 to time 2. And this would be a really good use for a paired t-test. So I hope that helped and that you're now able to compare the averages of two groups and assess whether or not they are statistically significant. Good luck.